presentation comes from Giordano Mancini from E4.
Okay, thank you to the organizer for having me in this beautiful venue. I am Giordano Mancini, the CTO of E4. We are an HPC system integrator, as you may know. We work with many different vendors from CPUs, GPUs, storage. We try to assemble infrastructure that are good for a specific purpose or for a general, more bigger computing environment. Here you have a timeline of what we did since the company was started about 20 years ago. So just a few milestones. For instance, we installed one of the first ARM clusters in Italy and Europe. And then in 2016, we created Davide, that was another mixed architecture cluster based on open power and GPUs, and it was ranked in the top 500 in the Green 500. And one cool thing about Davide, it was that there was a custom PCB that we co-designed with the University of Bologna and Cinega, and we used this thing to start doing our work in monitoring and energy efficiency in HPC. There are a lot of other things, not only from the point of view of infrastructure, but also the fact that we are actively participating in different European projects. Some have been concluded, a lot more are still running. For example, in the quantum computing field, in quantum docking, where we do co-design and validation of the methods, or in the porting from codes from one architecture to the other, for instance, from x86 to RISC-V. So there is a lot of things that we are involved with it. Of course, for a small company in Italy, we don't do this on our own, but we are involved with a lot of different partners from the industrial and the academic world. And just a few numbers of what has been happening the last 3 years, more or less. The company grew a lot. We were involved in a lot of different activities. New teams, including mine, by the way, were created. And so things are going quite fast. Of course, for a company like that, it was a good moment to be in the field because there was the AI explosion. But in my opinion, what is really giving the edge is the fact that previously we invested so much in the validation of the solutions. We have our own burning rooms, our own data center, and we do a lot of testing to prevent the don't-arrive problems to every system that we ship. And so this is what I'm going to speak about. Just a few considerations that not a problem. That I take from some milestones that other systems that we installed. Should I stop? Okay. And I will use this consideration to illustrate why we do this or this other activity with our own capacity in development. And so there will be a few projects. And then in the last part, I will speak about showing some results on benchmark on the European project side that, of course, we will use as a sort of wisdom to continue our work. So the first thing that we see in HPC that I want to talk about is not only the fact that we have growing power and growing demand for computing power, but also the fact that in many scientific fields, I just take 2 examples here, we have a lot of data that is coming from not from the bottom-up models, not from the theoretical sciences, but from the field sciences, from the data that we collect. I just here show 2 examples. One is cosmology, so I'm bringing the example of the square kilometer array, but there are other examples like that will come, like the Cherenkov array that we'll speak later, or in the future the ELISA interferometer. And you see how the amount of data that we have to store more or less permanently is growing. And the other field, we have genomics. Here we don't have giant installations like the telescope arrays. We have actually small machines that fit in a single lab, but these machines have a very high throughput capability of data. What we see here is not terabytes, it's terabases, but more or less you can get the approximation correctly. And you can see in the bottom graph how the short-read archive, so the archive of the NIH that stores just the kind of genomic data, has been growing over the year. And the problem with this data is that it can be short-read about every living species, but it can be humans. And when it's the humans, we have other problems of security and transparency of use. And of course, we have the problem. We have the condition that our demand for power is growing a lot. We know that we are really past the 1 kilowatt for a single platform, and this is growing very fast. And so the power that just a few years ago was enough for a rack, now it is not even enough for a single machine. And you see that this is a projection from the United Nations Agency for Energy. Just in Europe, the demand for the data centers is projected to grow a lot in the near future. Now, recently, maybe this is going to change for all disruptions, and there is already rumors about high-level decisions that we are going to reconsider the Green Deal. I don't know if it is a smart idea, but anyway, there will be a growth in the data center demand in the world and in Europe in the near future. And so what is the consequence? Is that we are not anymore focused just on the performance, on the time to solution, but on the energy to solution metric to decide how to run and to solve the problem. And we have that this energy to solution optimum may be different with the same hardware for different workloads, of course. And measuring it, collecting it, having statistics about it is not easy. We saw yesterday an example of how we have to delve in depth just with the GPUs to get the correct measurements, and we cannot just use what the simple interface is telling us. And so what all of this means for a 100-people company that works in HPC, it means that we have to create tools for ourselves, for our production that may scale on different situations, because we may be asked to create a small infrastructure, as I will show, or a bigger one, that we need our own monitoring solutions to be agnostic with respect to the technologies that you are validating and selling, and to expose all this knowledge to the customer and create the better possible solution given the constraints, given the budget every time. And sorry. So just a few words. This is how now we create a cluster. It is just an OpenStack on-prem cloud. We have a set of infrastructure as code tools that we use to create automation, to create the virtual machines, create the inventory, manage the secrets, do the monitoring, do the customization of all pieces of the infrastructure. I will just focus on two aspects, that is data and energy. So for data, we don't have our own storage solution. We work with many partners. I will just make two examples. We were the first to use NVMe-RAID solutions for BGFS. And for BGFS, we also created a monitoring solution. And this is an example of what we do in general. So try to create a ready-to-go solution that ships together the hardware, the software, the other components, validate it, and work with the partner to offer the higher-level solution. And for BGFS, we also released an automation pipeline on the Alcimo Galaxy. And similar work has been done with other partners, such as Limbit, for the RBD and Linstorm. So for instance, with Linstorm, we tested how much the load was on the performance. This is not enough. So what we did on BGFS, it's just a seed to create a more general monitoring solutions for all the kind of storage and for all the kind of platforms that we deal with, so that we can be third-party and agnostic with all of them. And the idea is to have the tools to measure not only performance or to detect anomalies, but also to provide other metrics, for instance, the energy and the carbon intensity. And we also have another tool that is not monitoring or alerting, but more a data lake for analytics that is called Hexamon. These things that I'm showing are all open source project, community. Argus is still in its infancy. The other one you can download, fork on the GitHub or contribute to. So Hexamon is a scalable, horizontally scalable architecture for monitoring and analytics. It can work directly with the sensors in the machines in the data center in band or out band, or you can put it aside whatever other tool you have, be it Ganglia, Bread Cluster Manager, whatever you are already using. And this is important because maybe you have different infrastructures in your data center. Each one has his own vendor, very good performing specific solution, but in this way, you have the continuity of data from one generation to the other. And with Hexamon, you can collect all the data together, run analytics and machine learning models, and do optimization at the data center level, as is what done in Cinega. So how we use all of this? Three very simple examples. The first is the pilot project of the Cherenkov telescope array that has been just this year finished in Tenerife. So we were asked to create an ICT to control the 9 telescope of this experiment. We basically built this together with the customer. We had a lot of requests because we had to stay in the budget, had to stay in a very tight energy and space budget, and provide the performance, especially for the storage that couldn't create a bottleneck. Most of the data is being analyzed real time, and then only a part is then, say, shipped to Italy for further processing. And we have to create an easy solution for the staff, maximizing use of technologies that the customer was already familiar with. So we customized our solution. For instance, the management part was done with Proxmox, but we put back a little of OpenStack in it for the lifecycle management. We changed a little bit our deployment tools to adapt to this new architecture. We modified from the initial request the networking and the other paths to be sure that everything was highly redundant, because one difficulty is that the Tenerife observatory is on the top of the Mount Teide, and this thing works mainly unattended. There is no HP staff 24/7 on service. And so we have to also allocate for spare parts to be stored on the place and a lot of other things. It was logistically very difficult. For the storage, that is what I was talking about it before, we used BGFS that was good enough for the demand, even if not super fast, but as I said, there were many constraints. And we use the other solutions that are common in this case. For instance, for the real-time analytics part, the INAF had it already on containers, so we installed a Rancher cluster that is running the analysis using Kafka and using Zabbix as a monitor. And so we just finished we are, I think in these days, just shipping the latest documentation. So this is an example of a small thing, because it's just 3 racks, but with a lot of constraints and difficulty that for a single company force you to create different tools, and so the same tools but use it in a different way. Another example is Franklin. It is a multi-generation thing. This is the situation that we found like 2 years ago in 2023. It was the first installation of this new team in E4, including me. And we did an update of the infrastructure using for the first time the architecture that I showed before. So based on OpenStack, based on the automation tools and so on. It became from a single architecture 60 node system, 100 heterogeneous, 100 node and heterogeneous cluster with the architecture mixed. And we added our own interactive computer environment to it. One difficulty was that there was a competition for a specific set of resources for molecular dynamics and for genomics. And we have to automate a way to provision the nodes in different way, not fully automatic, but semi-automatic, so that where there was a big demand, the node could be took out from the main pool and then put back in the main pool. And so it worked quite well, and it is the reason that the customer asked for a third incarnation of this thing. There will be another cluster that built on the Franklin experience. Once again, is based on OpenStack and our Medusa solution. There are different, a number of differences. BGFS is still on the scratch, but you have a bigger, vast data partition for general purpose. We have a list store for the control plane, that is another project, and so we just continue to innovate. And the bigger flagship project is the Galileo 100. This is a big public cloud for research in Cinega. Basically, we were, for the first time, prime contractor in this kind of procurement. We work with our partners, Dell, Data. There are a lot of similarities with what you have seen on the smaller systems, and this is important because we build on that experience before being able to apply to this kind of things. Sorry, just now last few words about benchmarks and the energy to solution problems. Two examples. The first is DFT simulation, ab initio molecular dynamics. This is an activity that we have been involved with in the framework of the Max Center of Excellence. Siesta was one of the code that was picked for this project. Is a code that is solving the Kohn-Sham equations, is a CPU code. Is with Fortan, it uses MPI upon MP, and it exploits the usual linear algebra libraries that we all know. So we asked what was the time to solution and energy to solution of running Siesta, just one case on different architectures. We have 4 architectures here, a RISC-V processor, 2 ARM CPUs, Ampere and Grace, and 1 x86 64 example. There are a few interesting but collateral considerations to be made. So, first of all, these are preliminary things, and we didn't have time to create a really homogeneous environment. So, you see that there are different compilers being used. But I think that the general picture is the same. And by the way, I want to thank my colleague Elisabetta for this test. So you see that RISC-V is still quite beyond the other processor. This is kind of expected, I think. But it's interesting that it is showing that kind of superlinear behavior, at least at few ranks. Meaning that probably when you increase the MPI ranks, you maybe do a better use of the cache or some other mechanism. There is also very difficult to perceive a small superlinear hump for Grace. On a general point of view, you have that Genoa and Grace are outperforming the other 2 CPUs, but the difference is not that big. But when you look at the energy that takes you to the optimization of the quantum dot, there is a difference about 35% more joules in the calculations. But this is not general because, I mean, this is a DFT calculation. Maybe you change the system or you change the basis set, you tweak somehow, and the picture will change. So I'm not using this example as a claim that Grace is better, just to justify the fact that we do that much work with the monitoring solution that is plug and play and third party with all the options that you have to the market. Another example on the same line, two examples actually, two different workloads, CFDs and an LLM workload. Here you have normalized to the reference value for the clock speed, the time to solution in the upper part, in the darker hue, and the energy to solution in the lower part of the graph. So, very simple. The time to solution, there are a few jumps, but more or less is smooth. The more you lower the clock, the more you wait. But for the energy to solution problem, you actually have a break-even point. And once again, it is similar but not quite the same for the two systems. And the gain is quite different. And once again, this means that if you really want to be energy efficient, you have to do a lot of testing if you know that you have a kind of more frequent type of workloads. This is all I wanted to say. Thank you for your attention. Just a few conclusions that, are already clear, I think, from what I said. Happy to answer questions or enjoy your coffee break.
Thank you, Giordano.